Hi there, I'm Alice. I'm one of the maintainers of Bevy. So, Bevy is one of the most popular Rust game engines, probably the most popular, and it's fully open source. We have thousands of users, we have hundreds of contributors, we have a thriving ecosystem of people doing strange and unusual things that I never thought possible. And as for me, I'm a maintainer. I help run the project, I help make it better, and a lot of my time is spent focusing on the ECS specifically, but also on making our documentation better and on managing the project and making sure everything runs smoothly. I spend a lot of time talking to users about their confusions and their needs, and I'm going to be using that experience today to try to explain how Bevy's ECS system can really work to meet your needs, rather than just being a tool you reach for performance. So if you don't know about Bevy, our goals are to make a highly modular engine where you can take only the bits that you want and keep the rest, where you can whip out the physics and replace it with your own physics. You can whip out the rendering, replace it with your own rendering. You can write your own first-class networking solution without needing to go and change the source code of the engine. And do generally very, very weird things with it. We're written in Rust, so it has to be blazing fast. And right now, but I think in general, we're going to be focusing on a code-first approach, where rather than using a WYSIWYG GUI to go and change everything in the engine, it's all just code. It's high-quality Rust code that you can test, you can maintain, you can hand to programmers, and for them to be happy and comfortable with it. But similarly, we want to support larger teams with artists, with animators, with the audio technicians to have a high quality asset reloading, hot reloading, and strong tools in the future. And the thing that sets Bevy apart from honestly a lot of its predecessors and a lot of competitors is that it's ergonomic. It's very comfortable to use. It's a joy and a delight to program in and to work with and to read. And to do that, we actually used ECS, this crazy structure of arrays performance tool, and used it as a central paradigm to define the whole engine around it. So I want to talk about how we did that and how it actually works, because a lot of people say ECS is a tool that's only supposed to be used for performance, but I don't think that's the case. So let's talk about some basic definitions for those of you who haven't seen ECS before. So ECS stands for Entity Component System, and there are three key parts to it. So first, you have the entities. So the entities, so you can kind of think of this as a messy database or table, like you see over on the right, where you have in the rows position, you have which entity it is. In the columns, you have which components, which data do they have. And then the entities basically just act as unique identifiers for those rows. You have the components, which will store the data, and then the systems, which will operate on all entities that have matching sets of components. That's the fundamental architecture, and it's very fast. But if that's all you've got, people will say, this will never work. You can't write an entire engine in the ECS. This is horrible. Because writing ECS code is terrible. If you've used Unity's dots, if you've used systems that came before it, they're often very heavy on boilerplate. They make the performance sensitive details very obvious, very in your face, and it's fundamentally too complex, too onerous and frustrating for the gameplay programmers who just want to hook up something to a door, and when the door opens, the boss spawns. And moreover, it's when you're using this previous generation of ECSs, you're constantly stumbling over these little tripping blocks. There'll be little things that you want to do, and you're like, how the heck do I do that? And the answer is, oh well, we didn't include that because it's not essential to make the physics system that we wrote this ECS for go fast. And so their opinion is, why would you use ECS if you don't need the performance? And I agree with them. If you have a last generation ECS, don't use it if you don't need the performance. This is a bad idea. But we're not the last generation. Bevy, along with the Flex and a couple of other modern engines, are an entirely different beast. I would call them the next generation of ECS. So something that you get a lot of the time is you'll have ECS as a component of an engine, where you have some sort of object-oriented layer, and then you have this ECS thing, and you try to stick them together and use the ECS only for like the heavy, performance-intensive, embarrassingly parallel parts of it, right? But this causes a lot of pain. And fundamentally, this causes a lot of pain because they are different, not because either part is bad. Because if you've worked with complex systems, complex software systems, if you have two different data models and they need to talk to each other in complex ways constantly, you're going to have all of your pain is going to be concentrated right at that translation boundary. And you'll have boilerplate, you'll have bugs, you'll have performance overheads, you'll have issues where where people just don't know both systems. You'll have things where something that you thought wasn't performance sensitive, you run a benchmark and you say, oh no, this dialogue system is now in our hot loop, oh god, and then you're like, okay, well, do I cut this dialogue system or do I rewrite it entirely in a different language? And that sort of translation adds a lot of time and a lot of friction and a lot of pain when you're developing big commercial projects. So as a result, because you have these hybrid systems where you have the object-oriented or whatever other paradigm, in addition to the ECS, people don't solve all of the tough use cases that to make ECS good enough. Because while it solves the parallel physics loop, then that's fine. So Bevy has decided that, okay, you know what, this sucks. We're gonna go and we're gonna commit to ECS. We're gonna say, what if everything was ECS? Which, you know, sounds crazy. But there are reasons for that. So ECS is fundamentally about cache locality. It's data should live beside its neighbors, and if the data lives beside the neighbors, you can make your code go faster because you're not jumping around all over the place constantly. But it's about a lot more than that. So if you have everything defined as components, and the components define what behavior applies to each entity, it becomes really easy to write gameplay systems for your game designers that create emergent behavior, like you might see in Dwarf Fortress. Or if everything is ECS, you have a unified control flow where everything follows the same paradigm. It's easy to learn, it's easy to reuse, and it's easy to optimize, because rather than optimizing each subsystem of the game, you just work with upstream and make all of the ECS stuff go faster. If you have everything that's living in a single data structure, the world we call it, you have really easy serialization and deserialization. You say, just grab this object, just write it to the disk. There's no custom serial, like Bevy's you can write generic save game libraries in Bevy, which is something that is that's almost like inconceivable in other places. You have this in ECS. You have this notion where you should decouple your behavior from your data, and it leads to cleaner, more maintainable code. But with Bevy, the thing that's really cool about ECS is its dependency injection, where you say, in this code, I want this data, and please give me this data. And rather than having to plummet down all the way through layers and layers and layers of function arguments, it just magically hands you the data that you want. And this is really like the star feature. And if you have all of this information about what types and data you need at each time in each system, the borrow checker is happy. But more importantly, you can have all of your systems running in parallel with each other based on what data access they need. And that's all defined at the type system level. And your systems just run in parallel with each other in a way that's guaranteed to be safe. So let's talk about the rest of this slide. Let's talk about some problems that you might see when you're trying to adapt a previous generation ECS to write your entire game in it, and some solutions. So here's an example, a couple of examples. One of them is from Amethyst on the left, which is a previous generation Rust ECS, and the one on the right is Unity. And there's a lot of arcane symbols here. There's a lot of repeated boilerplate that you're writing over and over again. And this sucks, and it makes your developers unhappy, it slows them down, and it makes people afraid to use your tool. And Bevy's solution is we're going to go and we're going to sprinkle a little bit of magic pixie dust from courtesy of the Rust ecosystem to make it just work. You write a function, which is just a function. There's no macros, there's no annotations. It's just a function. You set up your function arguments, and you say, okay, we need this type, and then the ECS will look at those types that you put in your function arguments and say, oh, you want this data in this system, and then when you add it to your schedule, it will just fetch that data out of the world and pull it into that system and run it every frame. And it's all powered by Rust's fantastic trait system, fundamentally. And you'll have things like automated caching of queries. So then from frame to frame, everything will continue to be fast. So suppose we have an ECS and we're using it to define behaviors, and we say, okay, we want to. The classic example is you have everything with a transform and everything with a velocity, and then you make it move like that. But the data that you have and the data that you actually need doesn't always match perfectly to the behavior that you want. So like a player-shaped entity may look a player entity may be shaped very similarly to an enemy entity. They may have exactly the same actually useful data, but you don't want to have your players behave exactly the same way as your enemies. And we could go and we could store something that says, okay, here's our character type component, and then we'll go and match on that, and we do things that look an awful lot like object-oriented programming. But this is going to make your code slow, and it's going to make your code messy. So in Bevy, and frankly, in almost every ECS, we have two components, two ideas that really help with this. So the first is we have marker components. These, or sometimes called tag components, they don't hold data. They're this new type, like that struct enemy, and it doesn't hold any data. It just is a type, and that's what it does. And we use these dataless types, and we insert them as components, and they're used to differentiate between entities that look the same, but actually need to behave differently. And this becomes really powerful when we combine it with our query filters. So you can see down below in the query ref life with enemy that you can say, I only want the life data, but I want to restrict it to the enemy, to those entities that also have the enemy component. And so you get to have some level of get to have really fine-grained, powerful control there, where the data that you need is separate from the matching set. So one of the other problems that comes up a lot when you're working with pure ECS is, okay, well, where do I put the things that don't really seem to make sense as entities? There's only ever going to be one of them. Like, do I store my game score as an entity? Do I store like how much lumber I have? Do I store like abstract things like tasks pools or audio handles like in an entity somewhere. And like rather than saying, okay, we're gonna go and make a custom like game object, mega object, it would still be nice to store this all in the ECS because then we get all the benefits, and especially the dependency injection. So Bevy has a concept that it calls resources. Resources are really easy. They're just global singleton data. It's, I only want one copy of this and store it in the world and then give it back out. And it's defined like everything else at the type system level. And they work exactly the same as entities, as components, except they're not stored on an entity. But similarly, you may have things where you want it to be an entity, but you only ever want it to be a single copy of that entity. And you could loop over your list of length 1, but this sucks and it's confusing. So we have a really simple API called query.single, and it says, fetch me the first object in this list and give me an error if there's not exactly one of them. And it's incredibly useful. And we spent a while debating whether we should add this because it's like, okay, well, why should we use this versus making something a resource? And the rule of thumb that we as a community have come to is that if it shares behavior with other entities, make it a singleton entity. Otherwise, make it a resource. So fundamentally, you have a lot of the things you might want to do with an ECS are often more complex than you might expect, especially as you add features and you might refactor. And the tutorial code often makes it look so easy, where you have a bunch of entities that you want to all treat the same way, and you have a nice, clear querying rule. But what happens if we want to have something that can branch, that can be composed, that can be powerful and expressive? Oh wait, we're making a query language. This is just a database query language. How do we do database query languages? And the answer is we use the type system, because of course we use the type system. We're going to go and we're going to write a query domain specific language in the type system. And there's all sorts of really cool things you can do with this. You can say, give me an option, a ref-t, which is to say, if this component exists, return its value on this entity. Otherwise, give me none. We can have has-t, which works the same way, except just returns true or false, and we can just branch on that. We can have things like any of. We can have or combinators. And then we have even more exotic things like trait queries, where you get all the components of an object that implement the specific trait, and it returns them as a trait object in your iterator. And this level of expressivity and power, it's hard to really appreciate until you've gotten yourself into one of those corners where you're like, oh man, if only there was a way to ask for exactly this data in exactly this way without having to go and rewrite everything or add some stupid hack. And by expanding the query system beyond really simple filters and component data requests, you have such a more powerful tool in a way that the previous generation of ECS doesn't. So here's a pretty simple problem. So suppose we're writing a collision detection problem, and we run our queries. We have two entities that have recorded. And how do we know which entities those were? Because if we're just allowed to ask for component data, we don't know which entities they are because it's just anonymous data. So what you can do in Bevy is you just add entity as another query item as if it was a component, and it'll just return that in your iterator like everything else. But this becomes a lot more powerful is when the question becomes, how do we actually use these specific entities that we've recorded? How do we actually do anything with that? We could go and we could write a for loop, and we could do a if entity equals this saved entity, then do this. But this is both slow and honestly kind of ugly. And at Bevy, we actually care about that. And the way that this works is Bevy's actually has very fast random access lookup for individual specific entities when keyed by their identifier. And this completely, once you figure out that this exists and this is a thing, this is the moment where Bevy starts to click. This is where you start to realize, oh, this is how I'm supposed to use this library, and it's not just all in order iteration. And so if you call query get or query get mute, you can access the data of specific entities in at one time. It's constant time regardless of how many entities there are. And so you get all of the benefits of a hyper-optimized vector for very fast iteration, and it also works like a hash map. And this is incredibly powerful. So something that comes up is you say, okay, I only care about processing this data when it's changed. So we have some system that will go and update and run and preserve some invariant, or maybe it will cache something, or maybe it will check for these changes, then propagate it out to somewhere else in the game. And it doesn't matter if we repeat this work, it would just do nothing, but that's wasteful and it's slow. And it would be really nice if there was some sort of like robust general mechanism for this, so then we don't have to like store, okay, here's the old copy of this data, here's the new data, and then we go and we check it, and like that's a lot of boilerplate, and it's really easy to screw up if you write it 100 times in a single game. And what Bevy does is every component, every resource, you can check if it's changed or not. And what we do is we have a timestamp mechanism where you say, here is the last time that this component changed. Here is the last time this system ran. How do these compare? And if the component has changed since the last time this system ran, then we go and we check and we say, hey, this data has changed, you may want to look at it. And it's really lovely when you combine this with existing ideas like query filters, where you can say, I want the data of component A, but only if the data of component B exists and has changed since the last time this system ran. And it becomes very, very smooth to write these really interesting, very gameplay relevant systems. So suppose we want to go and look over all of the entities and do exactly the same thing to each of them. In that case, we just want to do linear scans. This is perfect, this is easy, this is fast. But there's a lot of problems like collision detection where you can't do that. Like you will run into quadratic performance with millions of entities, or you may have or worse. It would be really nice if you could integrate things like quad trees directly into the ECS, or have some blessed pattern for it at least. But wait, ECS is basically just a database, right? It's a specialized in-memory database with strange performance characteristics, but this is just a database. These are just database indexes. How could we go and expand this idea into a first-class feature? And so these are indexes. They may be spatial indexes, but they may be ordinary indexes. And you can write a naive solution for them really easy. You use some sort of acceleration data structure, whether it's a hash map or whether it's a quad tree, and you map the values and the entities together. And then you just store it in a resource, and then you just ask the resource, okay, I want all of the entities within this region of space, or I want the entity that corresponds to this tile. And it goes and it looks it up and it fetches it. And this is a shockingly effective solution. It can make your game dramatically faster. But the problem with this is that Well, synchronizing state and cache invalidation is actually really hard, and when it goes wrong, things go very wrong because you say, oh, I want the entity for this tile, and it's actually the entity for its neighbor. Or you say, oh, give me all of the polygons within this region of space, and oh, that wasn't actually right, and then everything kind of explodes. And so something that I want to do in the future, and that the community wants to do, and I think is honestly an essential feature of a modern ECS, is first-class support for indexes, both spatial indexes and much more traditional database indexes that can rapidly accelerate these sort of common value-finding operations. So we're going to talk a little bit about the core underlying architecture of how ECSs work. So ECSs, they take your data, they transmute it into this horrible soup of bytes, and then they stick it as closely together as they possibly can, and then read the data with raw pointers. And this is great, except for the fact, and this data will be arranged into things called archetypes, where entities with the same components will be arranged close to each other because they're going to be operated on each other in similar ways. And this works really well, except for the fact that when you then want to go and move around this data, everything kind of has to get shuffled, and it becomes a very slow operation that breaks you out of the nice hot loop that you have. And in particular, if you want to shuffle all the data, you can't run anything else at the same time because, hey, I was busy using that. You're not allowed to go and change how that memory is laid out. So ECSs have this idea called commands. So commands are basically anything that you could do to the entire world, to all of the data that exists in your game. You can just turn into a command and say, hey, do this later. And they apply only at the next flush point. And in Bevy, we have the ability to control precisely when these flush points are scheduled arbitrarily. There's no artificial restrictions anymore. But then they also get evaluated at the end of the current schedule by default. Commands are a complex subject, and they're often very performance sensitive because you may have to go and spawn 10,000 entities for this frame, or you may want to go and despawn all of the effects from the bullet that you just shot, despawning. And one of the big things that you can do to optimize this is to batch the commands together, because the core idea of ECS is similar work should be done together. And if you have each of these commands, we're sending them one at a time. You're going out to the level of the world. You're going down, drilling down to the data, and then you go back out, and then you go back in, and then you go back out, and you do that 10,000 times. It's much easier if you start at the level of the world. You go in, and then you do the 10,000 operations. Then you step back out. Way less overhead. But in order to do that, you need to have some notion of what each command is doing. So command batching is on our list of interesting, cool future work that will make ECS better. So this is another very simple but very useful primitive. So it's often really challenging to know exactly what you're going to do when something happens. You may want to, suppose you have a collision. It's what happens when two objects collide. Who knows? Anything could happen when two objects collide. And if you're a library author, there's no way to write that all within a single system, because you need to expose something for other users to read. And the solution is pretty obvious. Just use events. And events are very powerful, and they're very easy to model inside of an ECS like Bevy's that has resources. You just have a list of things that happened, and you stick it in the resource, and then people read it out. Bevy's default event type is a multi-producer, multi-consumer. It's really simple, and it's double buffered, so you can read events from both the previous and the last frame. Works honestly very well. And you can see kind of some of the example of the syntax over on the left. It's you have an event reader, you have an event writer. But ultimately under the hood, like these are just resources. This is just ECS. But thinking about these tools and these extensions, it really helps bring together an engine and turn it from a tool that you use to make things go fast to something that you could see yourself writing an entire game in, where you could see all of the logic you could possibly imagine fitting inside of this paradigm. And when that does, it's like when you can fit everything inside of a single unified architecture, your code becomes so much nicer. So let's talk about other things you might want to do. So a really common thing that you get is you say, have this beautiful system that say runs your physics, and you're like, I don't want to run my physics all of the time. I may want to, pause the game. Imagine that, a game where you could pause the physics. And so we need some sort of abstraction for turning systems on and turning them back off. And we could go and have a core game loop, and we could say if game paused, then skip this part. Otherwise run all these systems. But that's not how Bevy works. Bevy doesn't have a single game loop that you write. You add systems to a schedule, and then they get run for you. But we could also handle the special case this in each system. We could say at the start of each of our systems, we could say if the game is paused, then return. But that's really easy to screw up. Like if you do this 10,000 times, then you have some systems that are running when the game is paused and some that aren't. It's going to suck. So there's a simple abstraction and a slightly more sophisticated one here. So the first one is run conditions. So before each system is run, before a task is dispatched for it and it gets run, we check some data from the world, and if that function that we call in the world returns false, the system just doesn't run. If it returns true, the system does run. And these are just ordinary functions that can access arbitrary data from the world in a read-only way, because Rust is cool. And it goes and it says, and you can use these and combine them to create these really complex behaviors in a way that saves you substantial performance. But when working with run conditions, there's actually another abstraction that's often quite powerful, where you have a state, your game as something of a state machine, where you have things that you want to do when you go into that state, there are things that you want to do when you come out of that state, and there are things that you want to do only when you're in that state. And so we have a fairly lightweight abstraction that does exactly that. You'll go and say, when you enter this state, run this system. When you leave this state, run this system for setup and clean and tear down. And then you have when I'm in this state, when I'm in the game playing, run all of these game logic systems. And this sort of flexibility and simplicity works really well. And you can do incredibly complex and powerful things with Bevy scheduling. You can create entire schedules of your own, and then take a system that mutates the entire world and run arbitrary game logic using branching and for loops and random numbers to generate what game logic you want. And it just works because it's all just Rust code. And something we want to support in the future is dynamic schedule modification, where you say, at runtime, I want to control which of these systems, what systems are in my game. This is controversial because we do a lot of work to initialize schedules and to ensure that they're valid. So this is not a tool you want to reach for all of the time. That's what run conditions are for. But if you want to do things like support game mods without forcing a reload of your game, or you really need to squeeze out the last bit of performance between levels, you can just do this. And then your systems, they aren't checked ever because they're just removed from the schedule. So this is talking about a very new feature that I helped write and was going to be shipped in the next Bevy release. And the core idea here is systems in ECS, they run every frame, and they're basically just polling. They say, hey, is there any work for me to do? Is there any work for me to do? Is there any work for me to do? But that's not how you want to write all of your control flow. Sometimes you want it to say, if this thing happens, then do this other thing, right? You don't want to be have 10,000 systems to be like, hey, did this button get clicked? Are you sure this button isn't clicked yet? And each of them will do different things, and then you have 10,000 pollers, one for each of your buttons. Like this is slow, this is complicated, this is kludgy. So if you have a game like Hearthstone, or you have something like UI, you want to respond dynamically based on the game state or player input. And you know, if it's a game like Hearthstone, or if it's a game like user input, it's just use scripting. Like just use scripting, send events, and read it in. But you don't have to use scripting. What if you could just write this all in Rust? What if you could write this all in ECS? And so this is the work that we're going to be shipping called one-shot systems, where they're systems that are run exactly once on demand. And this, of course, is completely heretical. It's controversial. That's not how systems works. That's not how ECS works. They go and they run and they check for work. But performance isn't always what you need. Sometimes you want this flexible, powerful, expressive logic. And if you go and you hook it into the ECS, you can write these things that work exactly like any other system, and you can just run them. You can say, hey, when this button is clicked, do this thing. Oh yeah, oh hey, we have callbacks. Like they're not incredibly slow, but they're not incredibly fast. But that's good enough for these complex one-off events. And I'm really, really excited to see what the community can do with them and what they can build in the future. So there's a couple more features here. We're getting into the more experimental, more advanced, more future work. So something that happens is sometimes if everything is ECS, you'll get things that probably shouldn't be interacted with by default, like your window. If your game window is in fact an entity, maybe don't despawn it recklessly. Or maybe you have something like this object is 5 screens away from the player. Don't try to simulate it. We want it to be sleeping. And so we could go and we could add a custom disabled component to our systems, which we want to then go and filter on all of those relevant systems to say without disabled. But that sucks. Remember having to write without disabled everywhere on all of your systems, otherwise you get these horrible, strange bugs, is bad. And fundamentally, the engine systems don't know about this custom disabled component that you have. The library plugins that you don't know about the disabled component you have. So how do we actually solve this use case for users? So what I propose is that there should be a special disabled marker component, and by default, queries exclude entities with that component. So you take the logic and ordinary logic and you flip it on its head, because you want the default behavior to be correct, and then this solves all of those ecosystem compatibility problems. But at the same time, if you say with disabled, it'll show up for you, right? And then you could go and you can inspect it, you can re-enable it, you can go do strange things by running game logic on disabled entities. And this isn't a new idea, but it's very powerful, and I think it's honestly an important and valuable part of what makes an ECS actually useful for users. Existing work also uses this for prefab entities, so entities that are already made up, and you can just quickly copy them and say, I want to spawn another goblin over here and make another tower, place right there. And so we still need to implement this in Bevy, but this is one or two pull requests. This is hey, if this is cool, you could do it. And ultimately, I think that users should be able to make their own components that work this way. They can just take the component trait and they can just add we can just add an associated type that says, is this opt-in or opt-out? And then they can have their own components that work opt-out. And by doing so, it'll work with all of the other stuff in the ecosystem automatically. And so we get to the final and most complicated feature. So ECS is really good for storing objects that are flat. But what happens if you need to go and reference other things in those entities? So if you're clever, you might be like, oh, that's easy. We'll just make a component that stores an entity inside of it, and then we can use that basically as a pointer, but like as a keyed pointer to things. But what happens if that entity is despawned? What happens if we want to make sure that all of our relations that are defined this way form an acyclic graph, or form a tree, or like have this other very important consideration? Do we go and validate it every time and then panic if it breaks, or how do we do this? And fundamentally, when you have these graphs, you want to walk around on graphs. You want to get the parent of my parent, or you want to go and say, for each of my descendants, my recursive descendants, go and do this operation. And this sucks, and it's painful, and there's no way to abstract over them between different relationships of the same, different relationships that mean different things. We could have a single parent component, which is what we currently do. We have parent and child. But if you want that to mean different things, it becomes very challenging to implement efficiently. And so this brings us to I think, the frontier of ECS systems. This is something that Flex by Sander Martens has really pioneered. The idea that we could take this idea of a component that points to another entity and make this a first-class feature of the ECS. And we could do this in a way that's ergonomic, in a way that's fast, in a way that's robust, where you could have mechanisms for, I want to get my parent, or I want to get my parent's parent, or I want to look at things, I want to do a depth-first search or a breadth-first search. Could be first-class built-in algorithms to the ECS, and they could be very, very fast. And this is something that we've been exploring actively within the ECS development community, and this is something I'm looking forward to the next talk that I give about ECS to be about relations and why they rock. But because Bevy is so incredibly modular and so incredibly hackable, somebody took the public interface of Bevy and they added relations to it, which is completely ridiculous. And I'm looking forward to learning from that, and I'm looking forward to extending and optimizing them, because I think that ECS can be used for entire games, and I think that this is the final missing piece. So that's all I have for you today, and I want to go and I want to say that the people who are like, you're crazy, you can't write a game entirely in ECS, it's just a performance tool. Those people, they were right. But I don't want them to be right anymore. If we go and we take our engine and we unify it all into a very nice ECS framework, you get performance for free without having to think about how to make your code fast. You get these beautiful and intuitive emergent mechanics. You get a single stack for gameplay and engine code that all looks the same and is very easy to read and modify. You have you can make awesome intercompatible ecosystems, and you have this incredible developer experience. So that's all I have for you today, and thank you so much for listening.